Hello, I am Zahra Zahedi and I'm going to present this paper with the title of To Monitor or Not Observing Robots' Behavior Based on a Game-Theoretic Model of Trust. Generally, when we have a human and robot team in which the robot is a worker and responsible for making and executing a plan, and the human is manager and is responsible to make sure that all the goals are achieved and all the metrics are met. Human can choose to continuously monitor the robot and its execution and intervene whenever it is necessary. But continuous monitoring is costly and human needs to spend many resources for this monitoring. Also, human can choose to not observe or monitor the robot, but in this condition, the human allow the robot to deviate to an unsafe or inexplicable plan in which it cannot satisfy human metrics and standards. So choosing not to observe the robot necessitates having trust on robots. But what if the human doesn't have trust on the robot? What human should do to both optimize their observation strategy and resources while ensuring that the robot stick to the safe or explicable plan while they don't have trust to each other. So if the human can have a strategy over observation in a way that sometimes monitor the robots and sometimes not monitor it in order to optimize resources while ensure that the robot always stick to the safe plan or explicable plan, this problem can be solved. And this is exactly what we investigated in this paper. Now, according to what I said, we can say that here the robot has two plans, a safe or explicable plan for all human observers and a probably risky plan or a probably inexplicable plan. Why we call it probably risky or inexplicable plan is that here we may have different type of human observers where some are some are stricter than others. So some human observers may be completely nitpick in which just consider one specific plan safe or explicable, and some may be less strict where a few deviation from the safe plan is considered safe for them. So the robot in these conditions may have a plan which is considered safe for all kind of human observers and a plan which may be risky and is considered unsafe for just some human observers, not all. The question which comes here is that why the robot should do unsafe or inexplicable plan at all. The answer is that firstly the robot doesn't know which kind of human observer is observing it. So it doesn't know for that specific human observer this optimal plan is considered safe or explicable or not. Apart from this, the robot has some side goals. This side goal can be the robot goal, like charge, and the robot wants to charge itself, or it can be related to the point that there is a service provider and the robot is trying to provide the service for that. To make all the things that I said clearer, let's talk about an example. In this example, which is a robot delivery domain or robot delivery example, the robot should take coffee and parcels like electric devices from different locations such as kitchen and reception to the employee desk. And given the sequential of decision-making problem, the robot can come up with two plans, PyPR and PyS. Let's talk about PyS. In PyS, the robot first goes to the kitchen take the coffee and bring it to the employee desk, and then goes to the reception, take the parcels and bring it to the employee desk. We can say that this plan is executable and is considered safe and explicable for all human observers. So if we consider that each human observer has a specific model of the robot, this plan is executable in all set of these models. Or we can say that it is safe in all set of different kind of human observers. And for PyPR, the robot first goes to the kitchen, take the coffee, then goes to the reception, takes the parcels, put all in the same tray and bring all together to the employee desk. As you can see, this is optimal plan for the robot because it doesn't need to go along the long corridors twice. But this plan is considered safe or explicable just for some human observers and unsafe for others, because some human observers may think that this plan is unsafe since the coffee may spill off the parcel and ruin it. So we can say that this plan is executable in subset of different human model of the robot. So if we have if we consider that we have two kind of human observers, we can say that one of the human is okay with both plan and the other one is just okay with PyPS. Also, in this example and in general, human can choose between different things. First, the human can choose to observe the plan. Well, if we consider a human observer who just considers PyS a safe or explicable plan, so human by observing the plan, if they see that the robot has chosen PyPR for execution, the robot will not let the robot to execute this plan. Or secondly, human can choose to not observe the plan but start observing the execution of the plan. So if the human observer is the one who just considered PyS as explicable, and if the robot chooses to execute PyPR, the human observer, as soon as observing the robot after taking coffee is going to reception for taking parcel, will realize this is not a explicable plan and will stop the robot from executing the remaining of the plan. Or finally, the human can choose to not observe the robot plan or execution of the plan at all. So the amount of trust human has on the robot will increase from up to down. Because, for example, choosing not to observe the robot needs having trust on the robot. Now, we can put all of these into a game in which the robot will have two actions, PR and PyS, which are the plans. And the human have three actions, which are choosing between observing the plan or execution of the plan or not observing at all. But since we have different kinds of human observer, for each specific kind of human observer, we should have different game metrics, which make our game a Bayesian game. What we did here is that instead of having exponential number of human observers with exponential number of game metrics, we can have just one game matrix in which for some cost values the cost is changing. I mean, we have some costs which are changing according to different type of human observers. So those costs can be random variables which make our Bayesian game, and each random variable shows a specific human observer. So if we look at the matrix game, we have defined CG VIH, IPH, and IEH are the costs that are random variables, and each of them are related to the point that different human observers with different models will stop the robot in different parts of the plan and will incur different inconvenience for not observing the explicable plan or safe plan. Also, if you look at our game, there are a bunch of different defined costs, which are related to the cost of making or executing a plan for robot and cost of observing a plan or execution of a plan, which is related to the human. But for the sake of time, I will not talk about them. Now, if we come back to the trust in this game means that the human observer always chooses not to observe the robot, and the robot will always make and execute the safe or explicable plan for that human observer. But generally, trust has meaning when the robot and the human has many interaction with each other and have prior knowledge about each other. So trust in one interaction is impossible because they don't have any prior knowledge about each other. So in no trust case, how human can optimize the monitoring costs and resources while doesn't have prior knowledge about the robot? What should human do? Well, the reasonable way for both of them is that to play pure strategy Nash equilibrium, in which the robot play the strategy which is pure, which is Nash equilibrium, and the human also play pure strategy Nash equilibrium, because when they choose their strategy which is pure strategy Nash equilibrium, they can ensure that by choosing that strategy none of them will deviate from that strategy. Although we prove that in our defined game with very high probability it doesn't have any pure strategy Nash equilibrium. So the existing work on trust doesn't work for our case. Our game doesn't have pure strategy Nash equilibrium because for any strategy either of the players choose, the other player has incentive to deviate from that. So we will have a circular loop in strategies which each player has incentive to deviate from that. Also, mixed strategy Nash equilibrium doesn't work here because if the robot plays probabilistically over different plans, it cannot guarantee safety for all kinds of human observers. Because of this, we introduced the notion of trust boundary, in which the human, by having probabilistic strategy over different observation strategy, can ensure that the robot will always stick to the safe or explicable plan, so that human can optimize resources while ensuring the safe plan. For this purpose, it means that the expected utility of the robot for the plan pi s, which is the safe plan under human observation strategy, should always be more than the expected utility of the robots for the plan which is probably risky under that observation strategy. This equation gives us a boundary in which human, by choosing the probability of observing or not observing from this boundary, can ensure that the robot will always do the safe plan. For example, for the robot delivery example, the human can choose QP, which is the probability of observing the plan, and QE, which is the probability of observing the execution of the plan, in a way that satisfies this equation. So these values will give the human what amount of time they should observe or not observe, and the robot by this strategy will stick to the safe plan. So for the experimental setup, we can use the robot delivery example that I mentioned and solve two robust planning problems which are in PDDL or annotated PDDL in order to compute the values associated with each defined cost in the game. And also, as I said, we have some costs which are random variables, and we choose random variables with normal distribution as we define here. We can write all of our random variable cost as a function of one of the costs, for example CG tilde R. So we just will have costs of not achieving the goal, which have different values associated with different kind of human observer. By having the matrix with values, we can compute the equation for trust boundary. So for any value of random variable CG tilde R, we will have an equation which gives us different trust boundary for different human observers. For example, by plotting this equation for different values of CG tilde R, we will have this figure. That the red line shows the trust boundary for this the human observer with this cost, and the blue line shows the boundary for the human observer with this cost. So this human observer, by choosing any probability upper this line, can ensure that the robot will stick to the safe plan. Also, this is true for this human observer. And any probability this human observer choose upper this blue line will ensure that the robot will choose safe plan. And between these two lines, it may be different line associated with different type of human observer with different boundary of the trust. And by intersecting all the region for different human observer, we will have this region. So all kind of human observers, by choosing their observing strategy in this region, can ensure the safe plan from the robots. To conclude, we model the notion of a trust a human supervisor places on a worker robot by modeling this interaction as a Bayesian game. Also, we show that the existing notion of game-theoretic trust breakdown in our setting due to the absence of pure strategy-Nash equilibrium with very high probability. And we introduce a notion of trust boundary that optimizes the supervisor's monitoring costs while ensuring that the robot worker will always stick to the safe plan. As a future work, we have planned to introduce more flexible notion of trust in repeated interaction setting. Thank you for your attention.